for us, and this is where that discussion earlier comes in. This is going to be huge for us. That's the total. That's the error or the within, and that's the model. This number right here and this number right here are extremely important, and they're going to be important going forward forever and ever and ever. This is a measure. We want this number to be as big as possible. We're going to try to design our experiment to get as many degrees of freedom to estimate the error, because this number is this number. Let that sink in. This number here, SP squared, is equal to this, to the ANOVA, and that's going to really mean something when we hit regression. But when we come over here and we say, hey, we're assuming that each of these have the same standard deviation. When we're assuming that this group 1 and group 2 and group 3 all have the same standard deviation, or square that, the same variance, we're assuming that all 3 groups have the same variance, that's my estimate of that variance. And that goes for all of them to get that number. Cool. Again, just keep in mind, I'm planting a seed that we want this number to be as big as possible. Why? Because we'll be dividing by more to get our error down. Of course, we may be adding some sum of squares, but we want to have the most data to estimate our error, which increases our power, because notice what it also does. When I increase that number, it increases this number. And when it increases that number, it shrinks this thing. It pulls the area out of the tails. It makes, just like it did for the t-test, it makes our test more powerful. I'm going to have all kinds of all kinds of examples that bring that together. So,
Professor, 2 is the numerator, 6 the denominator?
I'm sorry, one more time.
Is 2 the numerator and 6 the denominator?
Yes. That's the numerator degrees of freedom, and that's the denominator degrees of freedom. That's right.
Okay.
2, the model degrees of freedom is the numerator degrees of freedom, and the error degrees of freedom are the model. And actually, while I'm there, and brings up one more good point, is this guy here, notice that's the MS of the error, right? Mean square error. That's the MSE, which again, going forward, is a huge, is very commonly used. And I'm about to show you that here in just a second. If I take the square root of that, I get SP. That's known as the root mean squared error, for obvious reasons, RMSE. So this number here is that. If I take the square root of that, I get my estimate of the standard deviation, which is 2 in this case. Let me show you how you would get that quickly, though, in SAS. Oops. Here. Okay, so here is the data that we have. I put this on Blackboard if you want to, or Blackboard, on Canvas if you want to follow. So I just called this ANOVA CT. Forgot why I called it CT. But anyhow, that's the name of it. And then what we're going to do here, and actually I'm going to create the class here real quick. So class group and model run. So this class group is saying, hey, don't treat 1, 2, and 3 as numbers. Treat them as the names of groups. I could have called it John, Nancy, Sally. In an ANOVA, the 1s, 2s, and 3s are just group names. They don't have to be interval level or ratio level variables. They don't have to be continuous numerical variables. Have them. It could have just as easily been red, blue, green. So that's why I have class here. Class says, hey, treat those as categories. And this is saying, hey, let's try to model X from these categories. Can I learn something about X by telling you what group it's in? And so I run that. Oops, got to run all of it. And that looks pretty familiar, but what I want us to look at is this table right here. And all of that should look super duper familiar. And now, hopefully, we can read this very easily. It's just, that's our total. If we looked at all of the numbers minus the equal means model. That's the equal means model. And then this guy here is the separate means model. That's the residuals from the separate means model. That's the error that's left over after I let my model have my separate means on it. And of course, the difference in those two is the between sum of squares, which is how much you're explaining. If you started off with 462 and you ended up with 24, then you explain 438, and you divide sum of squares by degrees of freedom, gives you this one. Now I go horizontally, 24 divided by 6. By these two, we get 475, and you look that up either on StatTrak or in a table or on your calculator or in Excel, and you'll get a right-tailed probability of 0.0001. That's the probability. If there was no difference in means, the probability of seeing this big of a discrepancy by random chance or more extreme is very, very rare. So I'm going to say my assumption must be wrong. I'm going to assume my assumption is wrong. I'm going to conclude my assumption is wrong, that the equal means model is not our model. The evidence suggests that at least one pair of these means is different. And at least, judging from this picture here, we can say, well, if that's true, then at least 1 and 3 would be different. But maybe 2 and 3 or 1 and 3 would also be included in that. Another couple of things to look in here. Notice MSE, that's 4. Notice root MSE, that's your RMSE, that's your pooled standard deviation is 2. One more big thing to look at in here is this idea of R squared. You've probably heard of R squared if you haven't used it by now, but if not, that's fine. I'll introduce it to you here. R squared, and we'll see this again in the next in 2 chapters from now. R squared is the amount of variation that's explained by your full model. The percent, I'm sorry, it's the percent of, R squared is the percent of the variation that's explained by the full model. So what is that? Well, of course, if the full model explains 438 and there was 462 total, then the percentage of that is 438 divided by 2. If you want to take a calculator, divide 438 by 4, and you'll get 0.948052. And so that's just kind of, this guy here is, of course, our grand mean. I'll explain the coefficient of variation a little bit later. But that's good. For now, we should have all of these cells, really good idea of what these cells do. And that, I think, that's a lot of power because we're going to refer to those. This guy here, again, is the degrees of freedom. We want to pump that guy up. Cool. Any questions?
Yes.
On that?
Yes. The 0.94, could you go back to the chart, please?
Yeah, if I can, yeah, give me 1 second. I got to get this thing off.
Yeah, what is, R squared is explaining what specifically? The amount of variance.
Go ahead.
Okay. You first.
Oh. Okay, it's the percent of the variation in, it's the percent of the variation in the original observations that's explained by the separate means model.
By the separate means model.
That's right. So we only have 2 models, the equal means model and the separate means model. And the separate means model is explaining a certain percentage of variation, and the more, so a certain percentage of the variation in those from 3, 5, 7, 10, 12, 14, 20, 22, 24. We can calculate that variation, and that variation is reduced by 94.8% when we then look at what's left after the separate means model.
So that means 0.06 of the variation is not being accounted by the separate means model.
That's right. That's right.
And we don't know what's causing that variation then. Would we have to do some covariate or something to figure out if we wanted to figure out what the other...
Sure. Exactly. Now you're getting into regression. Exactly. So we have simple linear regression models, and we have multiple linear regression models. And so you would need another covariate or another explanatory variable, but it looks like just knowing what group they're in alone, right? Group could be, instead of 1, 2, 3, maybe group is, something that has 3 levels. group is, I can't think of anything right this second. Junior
T-shirt
senior,
size.
Okay.
T-shirt sizes.
T-shirt size. There's three things: small, medium, large. So instead of 1, 2, 3, we have small, medium, large. Just knowing what size someone's shirt is, in this case, might explain a lot of whatever the response is. So, maybe it's, I can't come up with things on the fly. Small, medium, large, and the response is how much somebody wants to
how about comfortableness?
Medium. Okay, sweet. Let's let 3, 5, and 7 be a rating of comfort. And we want to understand how comfortable people are. Our customers. Are our customers comfortable or not? And we want to know, well, does it look like their comfort rating is dependent on their small, medium, and large? Can we explain their comfort level? Because if we don't know their small, medium, and large T-shirt size, all we get is, hey, we saw 9 customers today. And we had a range from 3, which wasn't very comfortable at all, to 24, which was like super comfortable. And we said, well, that's a pretty big variance. That's a pretty big range. Us at the store manager, we'd like to get everybody up to the 24. So I wonder what that is. And they go look at men and women. And it looks like when I look at men and women, men have the 3, 10, 12, and 22, and women have the 5, 7, 14, and 24. So it doesn't look like there's a mean difference in the men and women. That's not explaining anything. And somebody goes, oh, hey, well, let's check out T-shirt size. Let's see if that can help us explain anything in this big difference between 3 and 24. And they say, okay, well, let's look. All the 3s, what were their score? All the smalls, what were their scores? Oh, theirs were 3, 5, 7. And all the mediums, what were theirs? Oh, theirs were 10, 12, and 14. And when the larges were the most comfortable, 20, 22, and 24, it looks like we're being able to explain some of the variance here. A statistician would say, oh, it looks like our within sum of squares is getting really small and our between sum of squares is getting really big, because by knowing the mean of the small ratings, my sum of squared residuals for that group is very small, because all those numbers are very close to that mean of 5. And so we say, okay, great. So it looks like in this case, if we let the explanatory variable be small, medium, and large, that explains a lot of variance. How much of the variance does it explain? It explains about 94.8% of the variance. It's not deterministic.
Now it became real.
Cool. Well, good work. You guys made it real. That was good. I should just probably put that. Maybe I'll put that in the bank. I'll write that on my sheet of paper here and bring up small, medium, large. That's awesome. But to your point, or to somebody's point, it's not deterministic. Knowing somebody's T-shirt size doesn't tell you what their comfort rating is. There's still a distribution. We saw 3 smalls. It was 3, 5, and 7. And at 3, 5, and 7, knowing small is not going to tell me what the comfort is, but it'll give me an idea of the distribution of what I should expect the comfort to be. And if it's small, I expect them to be down here. If it's medium, I expect a normal distribution of comforts. And if it's large, I expect another normal distribution of comforts with a mean that's higher than these two. But the standard deviation is assumed to be the same. All right.
So are we able to infer anything based on the R-square number?
At this point, the inference comes from our p-value, from our actual test. At this point, R-squared is just really a descriptor. R-squared is just a statistic that's interpretable. So here is where the inference comes from. Yes, there's a difference. This is essentially saying, yes, knowing small, medium, and large explains a significant amount of variation, and this is giving you some measure of how much that, some interpretable measure of what percentage of the variation that's totally there is explained. 0.94 is saying, yeah, it's a big predictor. But that's not saying you'll find in cancer studies that 0.0001, you might have a significant p-value, a very, very small p-value, and this R-squared might be only 8%. And that's just saying that it's, what's that saying? That's just saying that when that happens, that's because these numbers are much bigger, because our degrees of freedom, the power of our test is much bigger. and that this number isn't that much bigger than this number. But you'll have very, very significant p-value with an 8% R squared, which is very exciting to people who are studying cancer because they're not expecting to fully explain cancer, but it's really exciting when they find something that's actually related to it. Then they can make a drug and around that and make a difference. So good question, but just R squared alone, you could find a 0.88 R squared that had a not significant p-value here. So the R squared alone won't tell you significance. You got to look at the p-value and then look at the R squared to get a measure of how much you're actually explaining. Oops. So, awesome. All right. So we definitely covered that. Where do we want to go from here? I guess what I want to do is I'll rely on the videos for the assumptions for everybody for checking those assumptions. I want to encourage you to look at all of these PowerPoint slides. If you have any holes in your knowledge, I think these could significantly explain them. These are the assumptions. This is just from the book. This guy here. So, I mean, I can explain these. I can explain these further in office hours. Obviously, you're running out of time here, but these are very similar to what we talked about before. I guess I'll just talk about this. The ANOVA is very similar to the two-sample t-test, except when we're talking about the constant standard deviation assumption, notice this one's saying sigma 2 is equal to sigma 1. And if sigma 3 is equal to sigma 1, that means that all the standard deviations are equal. And in that case, these are the coverage probabilities of confidence intervals of 95% confidence intervals. And they're all right about 95%, meaning that those confidence intervals are the exact width that we need, or very close to the exact width that we need to cover the true difference in parameters. If we read this, this is actually a confidence interval, I think, for the difference of mu1 and mu2. But they could have picked any of the two. The point being that these confidence interval percentages are close to 95. Whereas notice when sigma 3 equals 2 times sigma 1, which means that sigma 3 is twice sigma 1 and thus twice sigma 2, that no matter what happens with the sample sizes, that the confidence intervals are too wide. And if the confidence intervals are too wide, then our critical values are too big. Because remember, the critical value from the hypothesis test is the same as the multiplier from the confidence interval. But again, double check that back with what we've done before. But notice these are 98, and when it gets worse, they're even still wider, then it's 99. And notice the difference that's in the two-sample t-test. The two-sample t-test was robust to this assumption of equal standard deviation when the sample sizes were equal, right? When the sample size, go back and check that, but when the sample sizes were equal, the t-test performed well. The pooled two-sample t-test performed well even when the standard deviations were different, when the sample sizes were the same. That's not true when you have 3. Through simulation studies, even when I have 10, 10, 10, all the sample sizes are the same. Clearly, when the standard deviations are different, we have problems with the coverage probability. So there's one more thing I wanted to show you that's going to help with your homework and that's going to be really useful from here on out. Actually, there's 2 things. You can check these. This is just kind of extra examples that you can check out. These are all, I've got the full SPOC one. I think these are really good to go through, but I want to show you one thing. Oh, that was it. The archaeology example. So this was our breakout. I'm really sorry we didn't get to it, and I hope to see, check out the office hours. I hope to see everybody in office hours this week. But, and Nibrat will hold his. But this is what I want to look at is this archaeology example. So, so let's check this out. Let's put it to use. So this is what we've got. We have discovered artifacts associated with the depths were randomly selected from the log of discoveries, not the log, a rhythm, but a log that's actually people writing stuff down. Since the artifacts and thus the depths are associated with completely different sites, it is assumed that the data are independent. So that's one of the assumptions of the ANOVA, is that we have independent observations. So we're just assuming that since our experimental design involves 3 different sites that are sufficiently spatially spaced apart from one another, we're just going to make the assumption that we have independent observations. So what do we have? These are our questions of interest. Are the means of sites 1 and 4 different? And what are we actually looking at here? These were the depths, right? Associated with the depths were randomly selected from the log of discoveries. So what we want to know, a lot of times in archaeology, the depth implies how old it is. The deeper it is, maybe how old it is. And we want to know, we got these 4 sites, is there any evidence that the sites are older than one another? So what we can do is look at the depth that they find the artifacts. Now, there's going to be some variance in the depths. Even if they're, from 300 BC, not all of the artifacts are going to be at the same depth. They're going to have some variance in it. Is the variance that we see, what we expect, is that consistent with the same depth, with the same age, or does that suggest that the ages are different? That's what we want to do. So we want to know about sites 1 and 4, sites 2 and 3, and then we'd love to know at the end, are sites 1 and 4 together different than 2 and 3 together? So let's see how we might be able to do that. And this is super useful. So first ask, is there reason to believe any of them are different? Why do I want to go in and start comparing all these little pairings? I can just test all of them at once all together. So I'm just going to run an ANOVA. And this is the reduced model. So this is the way that you can look at it as well. So instead of just writing HO, mu1 equals mu2 equals mu3 equals mu4, I can write it like this, where I'm just saying all 4 groups will be represented by the same mu. It's written 4 times, but it's the same character. That means the same mu. Whereas the full model, it says, well, let's distinguish mu1, mu2, mu3, and mu4 where they're possibly different. I'm going to fit different ones. This is the equal means model, and this is the separate means model. And I run my ANOVA, and it rejects. So on my board here, I'd have 4 groups. I'd have a bunch of different equal means model and separate means models, and I'd count up the residuals. To the equal means model, the sum of squared residuals would be 23,000. To the separate means model, the difference between the separate means and those individual observations would be 11,000, meaning I subtract those. I explained 12,397 sum of squared residuals. And it only took me 3 extra parameters to do it. Because notice, this is the equal means model, that's 1 parameter. And the separate means model needs 4, right? I got 4 groups now. So that's 4 parameters, mu1, mu2, mu3, mu4. So I had 46 observations. 46 minus 1 is 45. 46 minus 4 is 42. Subtract 45 and 42, and that's 3, and that's how many more parameters the full model has than the reduced model. I divide these guys, I get this guy. I divide 11,042, I get this guy. I divide these 2, I get 15.54. That's my that's my test statistic. I find out the right-tailed probability on an F3 and 42 F distribution with numerator 3 and denominator 42 degrees of freedom. And it gives me a p-value of 0.0001, which of course I'm going to reject. There is strong evidence to suggest at the alpha 0.05 level of significance that at least 2 of the sites have different mean depths. So now, if it failed to reject, your point's taken especially if I had 10 mu's. If I rejected here, I'd go, great, I didn't really accomplish much. I've got a lot more work to do because I got to go compare all these means. But if it failed to reject, I'd say, gosh, thank goodness I didn't start looking for difference in means first, when really there's no needle in this haystack. So that's one way you can look at the ANOVA. But we're on to the show. So question of interest here, are the means of sites 1 and 4 different? I'm going to take you through this and see if this makes sense. Notice that the ANOVA table compares 2 models. It compares, as we saw up here, it compares when you just look at it from SAS, it compares the separate means model to the equal means model. But really what it's doing is it's comparing a full model with a reduced model. It just so happens that the equal means model is the most reduced model you can get. Make sure that makes sense. The equal means model has 1 parameter. And you can't have a model with less than one parameter. The equal means model is the most reduced model you can get. However, I can use the ANOVA table. SAS, other programs will. It's tough to get SAS to do it, but we can make it on our own very easily, or we can program SAS to do it. But the point is we can get SAS to compare two models, a full and a reduced, where both of which, so key, where both of which are not the equal means model. What if I have two models that are hierarchical? One's a subset of the other one. I've got two models that I want to compare. One has a lot of parameters. The other one has less parameters. How can I compare those? Through an ANOVA table. So let me show you how you do that. So the reduced model here, if I want to test the sites of 1 and 4, just take some thought. So really ask question or focus, really just try to, I don't know, sometimes it takes repetition too. But this is how I'm going to do it. If I want to look at sites 1 and 4, then this is the reduced model and this is the full model. Notice the only difference in these two is that here, sites 1 and 4 have the same mean. And here, sites 1 and 4 have different means. Notice site 2 and 3 are the same in both models. They're going to add the same sum of squares. When I fit x bar 2 and x bar 3, they're going to add the same amount to both models down here in the within. So the question I always get, which is a really great question, is if I'm trying to compare 1 and 4, why in the world do I put 2 and 3 in the model? And that's because we're making the assumption that distribution 2 and distribution 3 have the same standard deviation as distribution 1 and distribution 4. So even though I'm not comparing the means of sites 2 and 3, I'm using their observations to get a better estimate of the standard deviation. Why would I throw those away when I can get a good estimate, a better estimate of the standard deviation, since I'm making the assumption that they are that their standard deviations are equal? I'm making the assumption that 1, 2, 3, and 4 distribution have the same standard deviations, so include the observations from 2 and 3 simply to get this number right here, this 42, or this 43 and this 42, to get those numbers to be bigger. Because if you take them away, you're going to reduce in. And when you reduce in, you're going to reduce this number. And when you reduce that number, you reduce the power of your test. And I'm just going to keep going over that. I saw a question. Was it Joshua?
Yes. How would you group them together in SAS so that you set them to be equal to each other, 1 and 4, but keep all the others the same?
How would you group them? So well, if you're going to do it, there's two ways to handle this. The way I might just need to focus on this way in particular, but to answer your question briefly, I think, is to, if you're going to put 1 and 4 together, you can just go back to the data set, and where you had determined that it was 1 and 4, simply change all the 1s to 4s, and you'll treat those as the same group.
Yeah, I was just asking because there aren't any of the SAS files used in here for the PowerPoints in Canvas. It's just the CSVs.
So you're saying the data's in there, but the SAS code isn't?
Right, you just have the CSV files, so we could do it.
Sure, but you're going to get a different answer. It's approaching it in a different. That's a different technique, is to just combine 1 and 4, because when you combine 1 and 4, now you're actually just dealing with 3 groups. So it's the same idea, but a different method. But that's certainly one way to do it, is just to go back to the data set and combine 1 and 4. But in certain situations that won't work out. So let me continue with this one, and then
all right, thank you.
I think that one will come up. But that's how you would do it. But this one here, what we're going to do is I just want to compare this model to this model. If the full model wins, I want you to think real quick. If the full model, if the evidence supports the full model, would that support mu1 and mu4 being different, or mu1 and mu4 being the same? If the full model wins.
Different?
Different. It would suggest that by letting group 1 have its own mean and group 4 have its own mean, that you're explaining a significant amount of variance. And so by letting them have their own means, that's evidence that they should have their own means. If, however, I force their means to be the same in this model, I force their means to be the same, then that is saying that there's no reason that they should have different means. It didn't explain a significant amount. So how am I going to do this? I need to find out how much each model is explaining, because it's very subjective, more or less. We already said that the full model will have a smaller residuals. So it's just how much significant it is. So this is what we do. We run SAS on the full model, and we run SAS on the reduced model, and then we get the sum of squares, and from that we build our own. So you're going to get very good at this. So this one, the top one here, is all the mu's. That's the equal means model versus mu naught, mu 2, mu 3, and mu naught. That's the reduced model, right? That one only has 3 parameters in it. Notice I've written 4, but 2 of them are the same. That's 3 unique parameters. And I'm going to compare it to the equal means model. I don't care about what this p-value is. I'm not running this ANOVA here for the p-value. I'm running it for the sum of squared residuals and for the degrees of freedom. That's the important thing here. So why do I care about running against the equal means model? You don't. I know it's going to win against the equal means model. The reason why I'm running it is to get how much is this model explaining. Because then my next step is to come over here and figure out how much is this model explaining. And check it out. When I let mu1 and mu4 be the same, the error that's left is 12,244. When I let them be different, it's a little bit less, 11,464. So what I want to do is say, with this model, it was 12,000. With this model, it's 11,000. For my extra parameters, for my extra 1 parameter, I didn't explain very much, but let's let the ANOVA do it. So what I do is I say, okay, this was the reduced model, so I'm going to take the 12,244 and put it down here. Because this is the reduced model. It only has 3 parameters. So I put that one down here in the reduced section, and it's got 43 degrees of freedom, because that's 46 minus 3. And then I say, okay, well, the full model, that's just simply the one with the more parameters. So that's mu1, mu2, mu3, mu4. So the full model has this 11,464. So that one goes in here with its degrees of freedom right there. Same game. Subtract. It looks like the full model, by adding those, by letting mu1 and mu4 be different, it only explains 780 degrees of freedom, or 780 sum of squared residuals, which wasn't very much. It's not the big amount that we saw earlier, especially compared to what's left in here. So that's what the ANOVA does. It says, oh, it's 780. It only had 1 extra parameter, so I divide 780 by 1, I get 780. I divide this 11,464 by 42, I get 273. I divide my mean squares, 780 by 273, I get 2.86. I look up now with an F1, 42, 1 numerator and 42 denominator degrees of freedom. I look at the area to the right of 2.86, and I get a p-value of 0.098. And so 0.05, I failed to reject the null hypothesis being that mu1 and mu4 are the same. And so that there's not enough evidence to suggest that site 1 and site 4 have different mean depth. That's how we can answer that question. Again, if I was you, I'd have maybe several questions. One would be, again, I don't quite know why these mu2 and mu3 are in the model. They're only in the model to increase that number. And just notice that if I took all the observations from site 2 and site 3 out of the model, I would have much less than 46 observations. And when I did 46 minus 1, 2, 3, 4 parameters, I'd have a much smaller number here. And when I divide that much smaller, when I have a much smaller number there, I don't have as much power in my test, because I don't have intuitively, I don't have as many observations giving me an estimate of my standard deviation. I have more uncertainty. And so great, and that's that. So that's site 1 and 4. When you go back and look at this, think about your breakout session was to look at sites, to now do sites 2 and 3. Use this data to test the difference between sites 2 and 3. How would you do that? Man, I really love to have had that breakout. And I know we're over here. I'm almost done. I just have two more short things to show you. But that is...
Professor?
Yes, please.
Quick question. And the reason that you want the more power is to reduce the probability of getting false positive and false negatives?
That's right. We want more power to reduce beta, to reduce the probability of, we're setting alpha. So the more degrees of freedom here, we still have the same alpha. We still have the same probability of rejecting when we shouldn't. So let's talk about that first, right? We set alpha to be 0.05. If the null is true, if there's no difference to be found, we're still going to find a difference 5% of the time that we would repeat this test. However, if I increase this 42, I increase the power of the test, which means I decrease the type 2 error. But let's define type 2 error. If I increase the power is the probability that I reject when the null is false, when there is something to detect. So when the null is false, when mu is different than mu4, I want the test to reject, and I'm going to increase the probability of that, meaning I decrease the probability of failing to reject when I really should reject. Sorry, what were you saying?
No, I was going to ask you for the definition. I know it was on one of the slides, but I hadn't memorized it.
Cool. Yeah, just the more you work with it, the more you'll get it. But yeah, beta is the probability of failing to reject when you should have rejected. And power is the probability of rejecting when you should reject. And type 1 error is the probability of rejecting when the null is true. Again, I really encourage, even at this point, if you did it before, to be able to draw that whole power plot, where you draw the null and you draw a possible alternative and shade the power and shade the beta and shade the alpha. That's a really good exercise. So if you've been thinking about it, here is the solution to that. That was the breakout. Here is the solution for if you were testing if sites 2 and 3 are different. I want to include 1 and 4 in the model. Why? Not because I give a flip about their means. I'm not testing 1 and 4 means. I don't care about that. But I am assuming that site 1 and 4 have the same standard deviation. So I want to include them in the model so that I can pump up my degrees of freedom error, because they're all estimating the overall error. And that's an estimate of the overall variance for each site, since I'm assuming them all to be equal. So that's why I'm putting 1 and 4 in the model. But I'm letting one model have the same mean for mu2 and mu3. You could easily see this as mu2 equals mu3, but I just code them as the same mean. And this one here is saying, oh, well, let's let them have possibly different means, or let's let them have different means, different x bars. And so I'm going to let these two, I'm going to throw these two in the ring and let them battle it out. And their battle is on who explains significantly more if they do sum of squared residuals. So here I go. I say, well, let's let this one. How am I going to do that? I'm going to do an ANOVA for mu1, mu0, mu0, mu4. And I see where that question was again. And I'll put this code out there, and you'll see. But yeah, I think I see where your question is now. In order to get this ANOVA, you're going to have to recode these guys as the same. So I see where that question was coming from now. In order to run this model, you're going to have to go back to the data set and make all the 1s 1s, all the 2s 0s, all the 3s 0s, and all the 4s 4s. And this model, you're just going to keep them 1s, 2s, 3s, and 4s. Mm-hmm. I'm sorry, I thought it was a different question, but yeah, in order to generate these ANOVAs, you're going to have to change the data so that instead of 1, 2, 3, and 4, you're going to have 1, and then 0, 0, 0, 0, 0, and 0, 0, 0, 0 for 2s and 3s, and then the 4s will still be 4s. And you'll get this. So here's the reduced model. I'm going to take that number. I'm going to run 2 ANOVAs. Only reason I'm running them is to get the sum of squares. I put that down here. This guy up here, I'm going to put right there. Notice that's the 42 line. I let them battle. They're almost the exact same sum of squares, and this one had an extra parameter letting 2 and 3 be different. But there's not much to explain. It didn't explain very much. And it's saying that you would almost always see something that extreme if there was no difference between 2 and 3. So there's not enough evidence, again, to suggest that sites 2 and 3 have different means. And so anyhow, the last question is simply this: now that we have run a test to say that 1 and 4, I'm going to call those B's, then we have a test to say that 1 and 4 are the same, and 2 and 3 are the same. All I have to do is run the equal means model versus the model with 1 and 4 having the same symbol and 2 and 3 having the same symbol in the data. And if it rejects, that favors the idea that 1 and 4 combined have a different mean than 2 and 3 combined. So I'll let you think about that, but these are just very clever ways of trying to get at different, what we're going to end up calling contrasts, which you'll see in Chapter 6. So you can go through these. What I want to show you, the last thing I want to show you here is this idea of Welch's ANOVA. I think you were introduced to it in the videos. The assumption of the ANOVA is that the standard deviations are equal. We've been through that today and we've talked about it. But just like there's a test that's robust to that assumption called the Welch's t-test, which is the Satterthwaite option, there's also a Welch's ANOVA. And that Welch's ANOVA is robust to the equal standard deviation assumption. It's not robust to the normality assumption. It still has the central limit theorem. So for large sample sizes, you can use for large sample sizes, you can almost always use the Welch's ANOVA to test means. But so a lot of times, as I said earlier, a lot of people only use the Satterthwaite, the Welch's t-test. A lot of people only use the Welch's ANOVA when they're testing means. And you can look at this. This is an example of, I think we looked at this once before. This example of why you should use the Welch's ANOVA over, if you're not sure of the assumptions, you should use Welch's ANOVA just by default. Where is my last thing I wanted to show you? Did I pass it? So these are all extra. Oh, there it is. Yeah. So here it is. So how do you run Welch's ANOVA? You can run it in proc GLM with data equals whatever your data is, class group, just like we did before. You have your model, and then under means, you can make this means call. So this is just a keyword. Means group is whatever your class, your categorical variable is. So means, it's saying take the means and group them, let them fit a different mean for each group. So it needs to know that grouping variable. Slash, I'll cover this this is like an F test. Don't worry about Hobb test equals BF. That's the Brown-Forsythe test. If you just took Hobb test equals BF out and just put Welch, Welch will give you this table. That's the Welch's ANOVA. So if you want to run an ANOVA, but you're not sure you have the equal standard deviation assumption, then run Welch's ANOVA and check out that p-value. Notice that the degrees of freedom have been adjusted just like it was in the Welch's t-test, but that's how you run it. And I'll cover that. I'll cover this Brown and Forsythe test a little on another day. But so for something like this, if I want to compare these three groups, small standard deviation, this is clearly visual evidence of different standard deviations. Get rid of the ANOVA, even if the sample sizes are the same. Get rid of the pooled variance ANOVA, and just run the Welch's ANOVA. Joshua, question?
Yeah, sorry, I locked my phone. Yeah, I just tried running the Hobb test equals Welch without the BF, and it gives you an error in SAS. It says it's expecting a bar left BF Levine or
yeah.
brain. So
sure, you got to
have to have one of those.
No, you got to take out Hobb test equals BF. BF
No, I took it out and it gave me an error. It says it's expecting something there.
Oh, really?
Yes.
Okay, hold on a second. Hang on. So if you come over here, do means group slash Welch. And there we go. So I think is this what you had? That?
Yeah, hog test equals. Oh, you mean take out the whole hog test?
That's what
Yeah,
I'm saying. Yeah,
just with
Welch
Welch.
is not a hog test. The hog test means homogeneity of variance test. Homogeneity of variance test. And so far, we've only used the F test. Just to show you, the hog test, this is a test of, let me just tell you why we're here. The hog test is a hypothesis test of equal standard deviation, just like the F test was. But this test is of all 3 or 4 or 5 or 6 different distributions. The null hypothesis is all the standard deviations are the same. The, I shouldn't say standard deviations. The null hypothesis is all the spreads are the same, because this one doesn't have the assumptions that the F test has. I always use the Brown-Forsythe test because it's assumption-free. The F test said all those distributions have to be normal. You can't use the central limit theorem to get you out of that. So the Brown-Forsythe test says, hey, let me check to see if all the if all the spreads are different. The null is that all the spreads are the same. The alternative is at least one group spread is different. And so I'll run this guy when I say hog test equals BF, and I do that, and it gives me this guy. And notice it's got this p-value of 1. Maybe oh, sure. So I always get a little suspicious with the sum of squares, but notice this p-value can't get any bigger than 1. But that's because I made this toy data, right? This data was a toy example. The standard deviations are the same for each one. Each one has the same sum of squares. Each observation has its own mean and one that's 2 away from it. So it's trying to estimate a variance. In order to test this, it's trying to estimate a variance of the variances, and the variance of the variances is 0, because each estimate of the deviance in each group is the same. But long story short, of course, with a p-value of 1, you're going to fail to reject. What are you failing to reject? You're failing to reject the null hypothesis that the spreads are equal. And clearly, that's visually what we have here. If this was less than 0.05, then we reject that and say that there's evidence that the standard deviations are different. Like if I said, hey, this guy is actually 240. Well, group 3 clearly has a much bigger standard deviation in spread than these other ones if I made that 240. And watch what would happen. I'm not even sure. Maybe it doesn't even have enough power to detect that. But clearly it looks like the standard deviations and the spreads are different. And my Brown-Forsythe test has got a smaller p-value, but it didn't have enough power to detect that. So hopefully everybody's saying, well, clearly that they are different, and I'm a little disappointed that the Brown-Forsythe test didn't have the power to detect that, but that's because we only had 9 observations. And that's that. But check out the ANOVA. The ANOVA still said, hey, looks like, there is evidence that those means are different. And we can run the Welch's ANOVA here, even though we have different samples, different spreads, because that's what Welch's ANOVA does, is it adjusts the degrees of freedom in just the appropriate way to have appropriate p-values. Okay, so we are way over, and I appreciate everybody sticking with me there. I'm glad we got the time to cover that in the beginning, because that is a very important table. And I'll send everybody equations. I think they were in the videos anyhow. Equations of the sum of squares within, sum of squares between, and you'll see how that n comes up. How that n comes up in here, where I tripped on the between sum of squares. But that's it. We said ANOVA. There was a lot to talk about, and no doubt. I mean, if you can make it to office hours this week, I imagine we'll have some good discussions there, and I can go over a couple more examples that I didn't go over here. But that's that. Anybody got any questions on the way out? Thanks for sticking around.
Just a quick question.
Okay.
So when the group, the example that you showed in which we had 4 different groups, and we were comparing if 1 and 4 are having equal, different means, and then 2 and 3 are having different. So in that, when we group 2 groups together, at the time also we have to check the assumptions, like if they are coming from the normal and their standard deviation. standard deviation will be equal, but normality, when we mix the groups up, that might be different, right?
That's true. Yeah, I mean, that's exactly true. If 2 and 3 are different, right? If 2 and 3 are actually coming from different standard deviations, I mean, if 2 and 3 are coming from 2 different normal distributions with different means, and you group them together, you might end up with a bimodal distribution. If they're the same, we're not going to have a problem with this one, because if there's no evidence that they're different, then when I combine obviously 2 observations or a bunch of observations from the same distribution, then of course you won't have that problem. But that's a very good point. Is here in this example, I'm just showing how to put those ANOVA tables together. But an important step would be to recheck those assumptions. Wherever it is, I think went too far back. It's right. These are just exercises you can check out to check understanding. You don't have to go through all these. These are just there for your benefit. But yeah, right here. Sure. When I put together 1 and 4, if 1 and 4 really are 2 different distributions, if one has a mean of 3 and the other one has a mean of 10, when I put 1 and 4 together, you'll probably have a bimodal distribution that humps at 1 and then humps at 10, which is obviously not normal. So you would definitely check that. Yeah. And if you yeah, I mean, so yeah, good point there. That's exactly what you would do. Any more questions? Shoot. All right. Sure? We're good? Awesome. Okay, everybody's looking good. All right, well, that's ANOVA. Very colorful. We will work on that on Sunday.
Hey,
cool.
Bivin, a quick question. If you don't mind, can you take a picture of the board and post it on
Sure.
the canvas, please?
Yeah. No problem. Yep, I've done that before. I actually know how to do that fairly quickly. And just looking around, so we can break out of here before the 20 minutes over. Great work tonight. Alexandra, I'm also a fan of what I think is Whataburger behind you. That is very appealing. I might hit that up right afterwards. And in that respect, all right. Again, I'm going to send out the equations for those so we can really feel what that is. But in the interest of Whataburger, Alexandra, will you break us out tonight? With the 1, 2, 3. Whammo style.
1, 2, 3, whammo.
Whammo!
Good work. All right. Nice 2-hour session there, guys. We'll work on that.